Hello, welcome back. It's been a while since I posted new content. I've been thinking about an issue or a problem having to do with large inverters, large batteries, and how to just handle 2, 3, 400 amps at 48 volts. So I've got one inverter. I'm backing up the whole house, but admittedly it's a little bit undersized. So what happens when you decide to upgrade? Stack inverters, maybe put an 18 kW Sun Gold. Now you've got a 20, 25, 30, 40, 50 kilowatt hour battery. You've got to manage 300, 400 amps, maybe 500 amps worth of power. I'm specifically referring to the type of battery management system that you'd need to use. Basically, they fall into two categories. You've got the all-in-one type. Here's an example of a very popular DALI BMS. They've got products that support up to 500 amps, or that's the claim. I'm a little bit skeptical of putting that much current through an onboard FET system. I think that there's a lot of heat, and I think that there's potentially a lot of problems. This is another popular all-in-one style BMS, Overkill Solar. Although looking at their website, they've only got a 100 amp model available. At least that's all I could find. So what, you need what, 3 of these, 4, maybe 5 of these? In fairness to these companies and the products they're selling, I'm not bashing them at all. I just think when you get into these higher amperages, there's better ways to handle it. My preferred battery management architecture would be one in which the BMS and the electronics are separate from the contactor, from the shunt, and from all the high current devices. Here's an example of a Batrium. I know Lithium Solar has investigated these products and reviewed them on his channel. This is a Chargery BMS. It does use separate power management module, which I certainly like, although the product itself seems a little bulky and a little clunky. It has been reviewed on several channels, so I'm not going to get into any details. Quick YouTube search, there's a lot of content on this product. This is a QUCC product. I'd consider this hybrid, as it is an all-in-one type unit, although it keeps the power separated out off the board. They don't use FETs. It's a separate power contactor. The Off-Grid Garage did a really thorough review of this product, and it's one of my favorites. But look at the power consumption on the relay. It's 250 milliamps. If you do the math on that, you're talking about 12 kilowatt hours a month. It's a lot of power. And that's a 200 amp contactor. If you upgraded to a 500 amp, 400, 500 amp, you're looking at a contactor that may draw as much as 300 milliamps on the coil just to keep the contacts closed for that much current. At that point, you're looking at well over 15 kilowatt hours per month of just wasted energy and heat. My preference is a system similar to what's illustrated here. It's a little more complicated in the wiring, in that the temperature probe is separate, the shunt is separate. You have a separate contactor that's not integrated. There's control wiring for all of these devices. And still you're left with the problem that the contactor consumes a fairly large parasitic load. In my case, I'm using a 200 amp contactor and my 120 amp hour battery. You can refer back to that original video. It draws 111 milliamps. That's like 4 kilowatt hours a month. It's an extremely large amount of parasitic power that's just going to waste. This is a Victron Battery Protect. It's a solid state relay, and it satisfies the requirement of very low standby power, but it's unidirectional, so you'd need 2 of them. That's about $200. I've got this Midnight Solar 175 amp remote trip breaker. It's based on Carling Technologies Type F breaker. It's pretty beefy. A 3/8 post, 24 volt trip coil, non-polarized, and it's a panel mount with, I think they're 1032 screws. The idea behind this is to use a single device that would replace two devices, that being the UL listed overcurrent protection and a golf cart style contactor, which actually has a tremendous parasitic load. So this 400 amp contactor draws 345 milliamps. You're talking about 12 kilowatt hours a month of wasted electricity. Of course, the battery I built before only had a 200 amp contactor in it, but it still pulls about 111 milliamps. I just tested it actually a little while ago. It's still 4 kilowatt hours a month. This particular breaker, it's a momentary coil. Unlike some of the other brands, like for example Eaton or maybe a Square D or Schneider type breaker, they're configured so when they trip, the contact inside opens and it no longer feeds power to the coil. Unfortunately, this particular product, it has a limitation for the number of seconds or minutes you can hold power on the coil without burning it up. So it needs a pulse to activate it and then shut off. So my solution is a circuit board. It's actually pretty simple. It's all analog. I've got a regulated power supply, 24 volts. Coming power from the BMS would come in between 18 and 75 volts. It regulates it down to 24, charges these capacitors, and then if the BMS releases, this relay is triggered and the power from the caps dumps into the remote trip coil and it shuts off. Now this is my really messy test board. I'm going to be using this switch to simulate the BMS cutting in and cutting out. I actually have a Ziva BMS right here, the same one that's in my 120 amp hour battery. But of course I smoked photo relays, so I can't use it. I'm going to need to repair it. In any case, this will simulate the condition. Turn it on. Capacitors charge. The green LED indicates you've got full charge. And if something should happen, BMS shuts off, and there you go, drops the load. And one more time, turn it on. BMS closes, board charges. In my way of thinking, this breaker probably is a perfect solution. It does have the downside that once it trips, of course, you have to be there personally to turn it back on. But here's the thing, most of the time your battery management system is only there as the final and last resort. If something catastrophic happens, you probably need to be there anyway. And there's the standby load. So we've gone from 111 milliamps in the case of the 200 amp contactor, or 345 in the case of the 400 amp contactor, down to 7. So now you're talking about a few watt hours a month. This is definitely the way I'm going to build my next battery. You said I'm thinking of like a 16S 2P using 310 amp hour cells. Just trying to save up enough money and decide which brand I want to get. If I want to go cheap, or if I want to pay a little bit more for a higher quality product. There's some pretty hot deals on Alibaba, but they're definitely off-brand cells, and I don't know if it's worth the risk. Now, I should mention, before the photo relays went bad on this board, I did test remote trip operation, and it worked fine. For anybody who realizes that a mechanical switch and a solid state relay are not exactly the same. Any type of semiconductor is always going to have some residual forward current, voltage drop or some leakage voltage. Fortunately, it's not a problem. The voltage does drop low enough when the SSR opened, and it releases this micro relay here, and it does remote trip, so there was no problem. Just unfortunately, I made the mistake of, you can see there's a missing component. According to the instructions for the regulated power supply, they were calling for a 680 microfarad filter cap, which is really not necessary because most batteries are going to have a pretty steady DC source anyways. That being said, I think the surge current on the capacitor fried these photo relays. Anyways, it was while I was testing this board that these relays went bad, so I'm assuming the surge was too great. I have a few parts left over and certainly could order more, so if anybody's interested in getting one of these boards, just leave a comment. I'm eventually planning on perhaps posting it on eBay for sale. I don't know what the price would be at this point. They're not terribly expensive. I think there's about $30 worth of parts on the board. The power supply itself is like $12, $13, $14.